drop a chat message and I'll be monitoring it on the side. Yeah, let's begin by explaining the first problem. So let's just jump right in. So problem one. Problem one is Besla motors. And so the setup of this problem is as follows. We are given essentially a graph, a general graph of like n vertices, like the standard like m vertices, m edges. I think n is less than 5 times 10 to the 4, and m is less than 10 to the 5, and we're given some parameter k, which is less than or equal to n, or less than or equal to 10. And then finally, we are told that basically there are c less than or equal to n of these. These are what they call charging stations. Furthermore, I should clarify this is the weighted graph. So there will be weights on these. There will be weights on the edges. And what we are interested in is we are interested in finding we want to find all of the non-charging stations, which I think the problem refers to them as like travel destinations, some other flavor text. But the point is we want to find all the non-charging stations that are distance r, or rather, to find all the that have rather we need to find all the non-charging stations that have at least they have at least k charging stations. You get that, yeah, charging stations that are within distance r, where r is another like input given. Okay, so I think I got all the constraints down. Yeah. So find all of the non-charging stations, aka the travel destinations, that have at least k charging stations within distance r from it. And we say distance, I'm talking about the shortest distance. Like if you were to run like some shortest path algorithm starting from some shortest path algorithm starting from a non-charging station to all the charging stations, you should get that at least k of them are within distance r from you. So how can we approach this problem? Well, this problem really actually is kind of centered around this one trick. And the trick is to observe. The trick is to observe that at least k, like the condition that we need at least k within R. This is equivalent to saying that the kth closest charging station is within R. Right? If you think about it, like if you have like all the charging stations, and you kind of sort like all of them with respect to how close they are. So you have the closest, second closest, third closest, up to the kth closest charging station needs to be within distance R. If that one's not within distance R, then you have less than k charging stations within distance R. And then on the other hand, if it was, then you would have enough. Okay. Why is this formulation easier to compute? Well, when you make it this formulation instead, you can instead just focus on computing the kth shortest paths from from different charging stations to reach all of the non-charging stations. So now, with this idea, we're going to run essentially a multi-source Dijkstra. So multi-source Dijkstra is similar concept to ordinary Dijkstra, except the idea is that we put all of the charging stations inside we put all the charging stations inside the queue at the beginning and initialize all of them. So yeah, we do multi-source from like all the charging stations to all the non-charging stations. So we have like some charging stations here, kind of put them all in the queue at the same time. And we need to figure out all of them are going to have some distances to the non-charging stations. And for each one we are interested in essentially, yeah, for each non-charging station, we are interested in the k shortest charging stations that can reach this station. So we run a multi-source Dijkstra, and we augment this Dijkstra to not just store the shortest distance, we store up to the k shortest, right? So we store essentially a two-dimensional array of like the distance for each vertex. We also store some like parameter, some j, which is basically tells us the distance from the jth closest charging station. So all we have to do is store like an additional parameter, basically store like a k-dimensional table for, or a size k table for each vertex that gives you that. So you have not only the closest charging station, the one with the shortest distance, but also all k with the shortest distance, right? And if we are able to compute this, then well, the rest of this is all of this is the way you compute this table is pretty much the same way as a typical Dijkstra. So in typical Dijkstra, you would visit some vertices, you would visit some states, and then you would kind of iterate over like all the adjacent. So if you were at this state, you would iterate over all of its adjacent, and you would like update these distances accordingly, and you put them into the priority queue if they're smaller, right? That's typical Dijkstra. It's a similar concept here, except our state is like we could be at a vertex, but we could also be like the jth distance or the j-1 distance or some other parameter. And then at each point, and then we kind of just update our Dijkstra in a similar fashion. So when we're at the state, we iterate over all the adjacent ones, and for each one, provided that that vertex we're trying to update does not already have a path from the same charging station, because we don't want to repeat duplicate charging stations. Like a charging station is able to reach a vertex with two different distances that are both the shortest, or that are like both the shortest and the second shortest. We don't want to count the second shortest as from the same charging station. It should be the k shortest from distinct charging stations. So we need to like differentiate that like we don't like update a vertex if we've already been visited from that same source charging station with a shorter distance. But as long as we put that condition in, we just update in the exact same way. So a quick outline is like if you start from this vertex, and let's say you update this one next. Now we see that I'm going to label these charging stations as like 1, 2, and 3. Now we say that from this non-charging station, the closest is 1, and maybe the second closest is like 2. And then after that, we use this one to now update this. So maybe see the closest is now 1, this closest is also 2. And then maybe there's another path from here where this is like 2, and this can also reach here. So it would also get updated here, depending on whichever one's shorter. But the important thing is we don't repeat 2 twice. We need to check if 2 already exists or is already able to reach this vertex when we try to update it the second time. And I think the actual problem, the edges are undirected, or the actual problem has an undirected graph, right? Yes, the actual problem is undirected, so you wouldn't have a situation like this. You would also have 3 would eventually be able to reach these vertices just with like probably the farthest distance, depending on what the weights are. So that's how that would be built. And then complexity wise, this will just be the same as a typical Dijkstra with our O of nk states, and we're doing m work per thing. So this would be the Dijkstra complexity, which is the O of m times k, because the times log of m, because the bottleneck of this is like when you're at each state, you iterate over all of its adjacent edges and update those states. So that if you for each vertex you iterate over all the adjacents, that is a total like n plus m work. The m, we'll say the m dominates, and then we say we do that like for each of j from 1 through k, so it's m times k times another log factor of. Actually, the priority queue could be up to a log of m times k. So I'll specify that. So it will be something like this for the final complexity. M times k times log of m times k, which, given that k is only 10 in this problem, that is a perfectly acceptable solution. So that concludes the first problem. Yeah. So really, pretty much the main observation you need to make is like that transformation of like, instead of looking at it from the perspective of at least k stations within distance r, you look at it as like thinking about the kth closest, and the kth closest is a more tractable problem that you can solve using a Dijkstra's algorithm, a modified Dijkstra's. All right. Yeah. Any questions before I move on to the second problem?